Okay, time's 2:30, so let's begin here. Project number 5 is due Friday at noon. That's all the announcements that I have. Are there any questions? Okay, we left off last time at about page 535. So we were talking about ways to evaluate the fit of a model, specifically models for chapters 2 and 4. And what I mean by evaluate the fit, I'm looking at, well, how good are our predictions of what we're after. So that means then we're going to be looking at residuals, and specifically we started looking at Pearson residuals last time. Again, these Pearson residuals are denoted as follows. We have E sub m, so that's our Pearson residual for the mth observation. And we take Y sub m, the observed value for the mth observation. So if this was binomial response data, this would be the binomial count. If this was Poisson response data, this would be, again, a Poisson count. We subtract off then what the model estimates that observation to have for a mean response. That forms our residual. But then we divide by the square root of the estimated variance of the response to take into account the variability that our response has. And so that we essentially have you can say a standardized value. So we looked at, for example, with the Placekicking data set at 21 yards, there were 20 trials. Remember, we put the data into what was called explanatory variable pattern form. And there was 19 successes observed. The estimated probability of success at that distance was 0.9676. So if we go through all the math, the Pearson residual is negative 0.4449. The farther this Pearson residual gets from 0, the more evidence there is that the observation is not fit well by the model. So we want residuals kind of close to 0. And as we talked about a little bit last time, and we will see again here shortly, that we essentially make like a standard normal approximation to this Pearson residual. Anything outside of maybe plus or minus 2 gives us a little bit of cause for concern. Okay. So now there's one problem with using this Pearson residual, and that is the fact that we are only dividing by the square root of the estimated variance of y. But if you notice, in the numerator itself, there's actually 2 random variables, not just one, y sub m. There's actually y hat sub m. That's a random variable too. And so ideally, we like to be able to account for all the variability that's in the numerator, and hopefully that will provide a better standard normal approximation. And in fact, it does. So the standardized Pearson residual, which we denote by r sub m, is exactly the same, except for look at the denominator here. Now we're having the estimated variance of ym minus y hat sub m. And that actually nicely simplifies to the estimated variance of y sub m, like we had before, times 1 minus h sub m, where h sub m is the mth diagonal value from our hat matrix. I would anticipate that there's probably a few of you who have not seen what a hat matrix is. A lot of you have. If you take a full semester of regression analysis, or if you take like Stat 970 or 971, you will see what a hat matrix is. First of all, let me just give you an intuitive sense for what this h sub m represents. It represents basically how far is this observation in terms of its x's? How far is it from, let's say, the center of all the observations in terms of their x's? So this value is between 0 and 1. The farther it is from 0, the more, let's say, outlying the x's are for this particular observation. And to put it into a simple linear regression setting, suppose here's x, here's y. Again, simple linear regression, so we assume our data comes from a normal distribution. And you might have a scatter plot that looks something like this. And if we plot the estimated regression model, will look something like that. Now x bar itself probably falls right about here. So the farther that these observations get from that vertical line there, the larger this hat matrix diagonal value will be, because it's getting farther from the center. Now the reason why that's kind of an important value, and we'll talk about this more later, is that the farther these points are, these points are out from the center, the more chance that particular point, or the more influence that particular point could have on where that regression line is drawn, and thus beta hat 0, beta hat 1. The farther the x's are from the center, the more influence that it could have. In particular, let me do a different color here. Let's say if I have a point that's down here. Also, so I add a point. What can happen? What can happen is that point will pull the estimated regression line actually down towards it. It has what's called leverage. And so this H has an important meaning in just regular old regression analysis, which we would talk about more later. But for now, just understand that it's a measure of influence. How it's actually calculated, just a second, how it's actually calculated is dependent upon using matrix algebra. And again, I know matrix algebra is not a prerequisite for this course, but I don't really see another way to explain it, or explain the actual calculation of it that's meaningful. I'm not going to ask you about matrix algebra on a test or something like that. All I expect you to understand is that, with respect to, here's where the hat matrix diagonal value is, and make sure you understand, it can measure influence. So, with respect to how this is actually calculated, let's let X be what's often referred to as a design matrix, if you've ever heard of that. And in the place-kicking setting, X would be a matrix that looks like this: a leading column of ones, and then a column of the explanatory variable values. So if I only have distance as my only explanatory variable, that's what my X matrix would look like. V hat is a diagonal matrix where on the diagonal, so like the 1, 1 element, 2, 2 element, and so on, are the estimated variances of y hat. So for a logis regression setting, that would be n times pi hat times 1 minus pi hat, where n is the number of observations of a particular explanatory variable pattern. And then the hat matrix then is shown there. So v hat square root x times x prime v hat x inverse x prime v hat square root. That all comes from, if you've heard of weighted least squares. So like one of the last things that I do when I teach a Stat 870 course, we talk about weighted least squares. This is a hat matrix from weighted least squares. Okay, so what this HM is then is the mth diagonal element of H. So H1 will be the 1, 1 element of H. H2 will be the 2, 2 element. I'm sorry, you had a question?
So are you talking about it in terms of distance from the mean of X or distance from the line?
Distance from the mean of X. It's a measurement of how extreme a particular observation is with respect to its explanatory variable values. So in one dimension, it's how far you are from X bar. In 2 dimensions, 3 dimensions, 4 dimensions, in terms of 2, 3, 4 explanatory variables, you can see it becomes more of a multivariate measure of distance. And the reason, again, why H is often a concern is because, again, it can cause your model to change depending upon where that point is and how extreme it is. So, I guess I am getting ahead of myself. So, since this point right here, since that's kind of following the same trend, while it will have a large hat matrix diagonal value, it's no big deal, because it's not going to really change your line. But this point right here, since it's far from X bar, and it's quite different from the normal trend, it will cause cause issues.
If you have a line exactly at X bar, but its value on Y is 0, it would cause just as much a problem.
It will have very little influence. It will have some influence, yes. So I think you're saying, let's say if I had a point right here, what would happen? Well, that line was just going to move down a little bit, but notice it's still the same slope. And remember, it's the slope that's really important in interpreting the effect that X has on the response. So, I mean, if you want to know more about hat matrix diagonal values, let me see if I do give a reference. Well, it's on my, I can't find the exact chapter. I believe it's chapter 9 or it's 10 of my Study 70 lecture notes if you want to see it more. So anyway, so there's the standardized Pearson residual. Now, both the standardized Pearson residual and the Pearson residual have approximate normal distributions to them, where the standardized Pearson residual will be better approximated by the normal. Okay? So what that means for us then is if you have something, if you have a, let's say a standardized Pearson residual of about 5, well, that would be very unusual to have, you know, with respect to a standard normal distribution. Because again, you expect most observations to be within plus or minus 2, maybe plus or minus 3 of 0. If you have one out 5, that should cause you some concern. And what that's indicating is that that observation is potentially fit poorly by your model. It's an outlier, potentially. I want to emphasize the word potentially there. So again, if you've had a full semester of regression analysis, you know, typically what you would do is, okay, you calculate these, you calculate what would be typically called standardized residuals, and you would compare it to these residuals to a normal distribution. If you have anything large in absolute value that says, okay, I have an outlier. Fortunately, it's not as clear cut here when we're dealing with logistic regression models, Poisson regression models, probit regression models, and so on. And the key is that this normal distribution approximation may not work well in certain situations. Here's why. And I broke this up into chapter 2 and chapter 4 models. So chapter 2 means that we're dealing with a Bernoulli or binomial response. What we're essentially doing with like a logistic regression model setting is we're doing a normal approximation to binomial random variables. And after all, what are we observing? We're observing the number of successes out of a particular number of trials. This approximation, how well it does, is dependent upon how many observations you have for a particular explanatory variable pattern and what the probability of success is. If you have a low n, the approximation is going to be poor. So I would even, so if n was 1, I wouldn't trust that approximation at all. If pi is close to 1 or close to 0, depending upon what n is, the approximation may be poor as well. Here's why. Let's say pi hat sub m is equal to 0.9 and n is low, 3. And let's just say for one explanatory variable pattern, of the 3 trials, we had only 1 success. But pi hat is 0.9, saying that, hey, there was a good chance of having successes here. Well, what would be the Pearson residual? Well, you can go through all the calculations, get negative 3.27. And if we would simply use a regular old standard normal approximation here, again, we would expect everything to be within all possible residuals, most of them to be within plus or minus 2, right? About 95% of them should be within plus or minus 2. 99% of them will be within plus or minus 2.576. This was negative 3.27. Does that mean that this is an outlier? That this observation is poorly fit by the model? Not necessarily. The normal distribution is obviously a distribution for a continuous random variable. A binomial distribution is for a discrete random variable. How many possible values of E could there be? 4. And when y is equal to 0, 1, 2, and 3. So E sub m actually has a discrete distribution with 4 possible values. But here we are using this continuous distribution, a normal, to essentially estimate the distribution. So just to show you what can happen, please note there was a small, looked like a little typo in the notes there. For some reason the dash or the minus sign was separated from the greater than sign. Well, let's look at what the probability distributions are for this case. Actually write them out. So let's say pi hat's 0.9, n is 3, and what I'm going to do is calculate the Pearson residual for all possible values of y. I'm also going to compute what's the probability that a standard normal random variable is less than whatever my value of E is. And I'm also going to calculate the estimated probability for a binomial distribution having a corresponding value less than y. So here are all my y values, 0, 1, 2, and 3. Here are the corresponding E values. Now using a normal distribution approximation, it says the probability of being less than negative 1.35 is 0.0885. The probability of being less than or equal to negative 3.27 is 0.0005. Now remember what we observed for this particular example. Y equal 1. And what this is saying is, if I could trust the normal distribution approximation, what this is saying is it would be very unusual to have only one success out of 3 trials if pi was truly 0.9. Now let's take a look at the binomial distribution. For that same case, when y is 1, now my probability is 0.028, probability being less than 1, or than equivalent negative 3.27 if I put it on the E scale. So now, while it's a little unusual, but it's not necessarily as unusual as we were having before. But look at some of these other probabilities. So the binomial says 0.271 for when y is equal to 2. The normal says 0.0885. When y is 3, the binomial correctly says 1, because of course you can't have anything higher. But look at what the normal says, 0.719. If this normal approximation worked well, we would expect the prob.norm column to be just about the same as the prob.bin column. We can see there are quite a big differences there. So, due to this discrete nature of our responses here, we cannot always trust a normal distribution approximation. So when will the normal approximation work? Well, let's say if you have pi hats that are kind of in the middle and a relatively large n. Well, what's large n? Well, a statistician never wants to tell you what, when you're for sure exactly safe. It is a complicated thing. The larger the n, the better, of course. But when can you start trusting it? Well, I don't know. I think you'll see some examples coming up that will help shed some light on that. I'm not going to say 30. I'm not going to say 50. I'm not going to say 100. It's all dependent upon exactly what pi is and what of course the corresponding n. So what I like to do then, with using a normal approximation here, is just use it as an initial look to let me see, okay, do I have potentially any problems? And then I always go back to my data and look, okay, I have n equal 2 there. well, I can't trust the normal approximation. I'm not going to worry about that then if I have a large Pearson residual and absolute value. Okay. So then another place where this can occur, and I was kind of alluding to this too, so let's say that n is 100. Now you might be thinking, oh wow, 100, yeah, that's a good sample size. But when you have a pi hat that's extremely close to 0 or extremely close to 1, notice what that means. While you still have 101 possible values that y could take on, there's only a very few of them that have any probabilities that are, let's say, greater than 0.01. And so because of that, a normal approximation there, in that case, is still likely going to be poor as well. What about chapter 4 models? So this is when we observe like a Poisson count. Well, fortunately, the issues are not as extreme here, as much of a problem here as they were with the chapter 2 models. And basically, you know, where you need to worry about is if you have, let's say, a y hat that's very low. And in that case, a normal distribution approximation is going to break down more. I mean, still, you're using a continuous distribution to approximate a discrete distribution. But the approximation is typically better unless you have an extremely low y hat. So as I say here, I will typically, and you'll see this in some plots that I do, put some lines on the plots at ±2, ±3 to help me make an initial judgment. Okay. Some comments. Okay, standardized Pearson residuals are better than Pearson residuals to look at. Well, why did I tell you about Pearson residuals? Well, you can see that they're very similar in terms of the equations, but there might be some situations with more complicated models outside of this class where calculating a standardized Pearson residual is much more difficult. Well, then you can always go to a Pearson residual because that's always typically going to be very easy to calculate. So that's one reason why I tell you. So in what situation would you expect n sub m to be approximately 1 for all your observations? In terms of, well, let me back up. This should be with respect to the chapter 2 models. That would correspond to a situation where all your explanatory variable patterns are unique. Meaning you don't have any, let's say, Bernoulli observations that have exactly the same set of x's. Or to put it another way, suppose you only have one x, one explanatory variable, and it's continuous. And all your n sub m's will be equal to 1. And in that case, using a standard normal approximation, it's not going to really help you at all. There are other kinds of residuals out there. In particular, there are what are called deviance residuals. And what it's based upon is the residual deviance. So can someone tell me what the residual deviance measures? We saw this in chapter 2 for the first time. It's a likelihood ratio. It's a -2 log lambda. Likelihood ratio test statistic, essentially, that compares what? Saturated model to what?
Our school model is estimated model.
Your model of interest, let's say. So it's a -2 log lambda statistic that compares your model of interest to a saturated model. Now, you know, if you look inside then that likelihood ratio, you'll notice that you know, essentially, you know, what you're doing is you have likelihood functions, the log likelihood functions, and those log likelihood functions are sums of, for every single observation, a particular component. And so if you look at it from a different perspective, you could rewrite your residual deviance like this. The sum of some quantities, let's call them D's, over your entire data set. Every observation contributes one term to the -2 log lambda statistic. And with that then, that allows you to define then this new kind of residual called a deviance residual, which is just simply the square root of d sub m times the sine of ym minus y hat m. What that means, if you've never seen that notation before, let's say y was greater than y hat. the sign will be positive. If y is less than y hat, the sign will be negative. So if y was 2, y hat was 3, you get a negative that you put out in front of that square root sign. That is a deviance residual. The farther this deviance residual is from 0, the worse fitting the model is to that observation, just like what we saw with the Pearson residual. And so if you wanted to, you could divide by the square root of 1 minus the hat matrix diagonal value, and you will get a standardized deviance residual. And you can work with these kinds of residuals just like what we did with the Pearson ones. I give a little bit more details in my book. Typically, I just focus on one set of residuals, usually it's just the Pearson ones. It's, to some respects, it's personal preference, but there are other opportunities and some stuff that we will look at that allows you to still kind of look at the deviance residuals too. So how do we calculate these kinds of residuals, or the Pearson residuals? Well, there's the residuals function. If you say type equal Pearson, and you get the Pearson residuals out. There's also an R standard function where you say type equal Pearson, you get the standardized Pearson residuals out. Here's a question. Suppose a normal distribution approximation does actually work and you have 100 observations. And everything is, and somehow you know that everything is okay with the model. Approximately how many standardized residuals would you expect to be outside of plus or minus 2? About 5. Yeah, because 5%. So I put this here on purpose because, you know, if you know, this normal distribution, standard normal distribution, you know, the probability that you're within plus or minus 2 is about 5%. I'm sorry, 95%. So there's about 5% that's okay to be outside. So just realize, just because you're outside doesn't mean, again, that's something to worry about. About how many would you expect outside of plus or minus 2.576? Plus or minus 2.576? Well, about 1. Okay, because 99% is within plus or minus 2.576. Now let's say let's go back to the plus or minus 2 again. You know, so what that basically is meaning is if I see something like if I were to graph a standard normal distribution here, kind of. Here's -2, here's +2, and let's say I do have 100 observations. You know, I might have another observation here, 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 and so on. So I got my 5 outside. Let's say I remove one of those 5, and I put it out there. Is this something to be worried about? I still have 5 of 100 outside of plus or minus 2. Is that something to be worried about? Yeah, because that's extremely unusual. So it's not just the fact that I got 5, it's their location that matters too. So let's take a look at some plots. Now, what you often do when you examine the residuals from an estimated model's fit is that you plot the residuals on the y-axis of a plot. And on the x-axis of the plot, you plot it against some important component of your data set or your model, such as maybe an important explanatory variable, such as maybe y hat. You plot it versus something. And what this does is allows you to evaluate 2 different things. First of all, do you have any, you know, any values outside of, let's say, plus or minus 2 or plus or minus 3? But also allows you to look for trend. Because if you see some kind of trend amongst your residuals, that might say, uh-oh, something's going on here. I mean, why do I always have small Pearson residuals, let's say, for low values of my, let's say, y hat? And why do I always have high ones for my high values of y hat. Maybe there's something wrong with my model. So that's why we look at two different things. Again, the plus or minus 2 or plus or minus 3, but also look for trends. So let's take a look at some plots. Standardized Pearson residual versus y hat. The red points are actually supposed to be little dots, although my pen sometimes moved a little bit. Those. So those are indicating standardized Pearson residual y hat pairs. And I've plotted plus or minus 2, plus or minus 3 there. So what we see here is essentially a random scattering of points. Let's assume that my normal approximation works. If you see a plot like this, what should you do? You should go, yes, my model works. It's working well. I don't have any, it doesn't look like I have any problems. So, next plot. Random scattering of points. Everything's within plus or minus 3. And let's assume the normal approximation works. What do you think? Is there any problems?
Not really.
No. No, again, as we just kind of got done saying, and sorry, I forgot to mention, we have about 50 points here. So, what we're seeing here is, yeah, we have a few outside of plus or minus 2, but they're still within plus or minus 3. As long as, and let's say the normal approximation works, yeah, this is to be expected. Even if you have a good model. Nothing to be concerned about here. So, now I have a random scattering of points. A few are outside of plus or minus 3, and let's assume that the normal approximation works. What do you think? I might start being a little bit concerned. I would probably want to look into some of these points, and maybe even some of these too. Look into them, look at them closer to see, maybe you can detect a reason why this is happening. We'll talk about what could be happening later. In section 5.4, we have a nice example that goes through from the start to the beginning of choosing a model and includes stuff like this. And I'll illustrate more about, well, what should you do when you have something like this? But at least what this tells me is that, yeah, I like to investigate this a little bit further. Let's take a look at those observations closer. Maybe I can figure out why this is happening. And maybe those points have something in common. If so, maybe it's you can include an additional explanatory variable in your data set to account for that. Okay. Well, here's another situation. I have a random scattering of points. Many more points than expected are outside of plus or minus 2. Let's assume a normal approximation works. What do you think? Should we be worried? Yes. Okay, so we're having some issues with our model's fit. We have a lot more variability amongst our residuals than we would typically expect. This could be a sign of something called over dispersion. So the name dispersion often means variability. Over means, well, you're over. You're, let's say, maybe higher than normal. So this could be a sign of what's called over dispersion. I don't have necessarily a trend here, but what I'm seeing is my residuals are more variable than they should be. And it could be a fundamental problem with my model. Section 5.3 talk about how to handle this. Now I'm not saying anything about my normal distribution approximation here. I have a trend in these points. I even indicated the trend with the purple line there, so in case you couldn't see it. So is this something to be concerned about? Yes.
Dr. Gilder?
Yeah.
What will the over dispersion mean for, what would it look like in the data set?
Well, I think it would be difficult for just let's say looking at the numbers of the data set to see it, if that's what you're talking about. I will talk about a little bit in section 5.3, but I'll give you a little bit of an example here to foreshadow. Let's say that we have, let's say y is a Poisson random variable. Okay. Now, if you remember with the Poisson, expected value of y is equal to the variance of y. Okay. Well, let's say that I observed, because in real life situation you won't know what the expected value of y is or the variance of y, but let's say that I observe my sample mean to be 5. But let's say my sample variance is called s squared, is 10. That tells me I have more variability than I would expect if I were to use this as a model, Poisson distribution as a model for my data. So I guess with respect to that, that's how you could see it. And you might be able to just look at your data, you look at all your counts, and you maybe you can see more variability amongst the y's than what you would be comfortable with. So more on that later. So I also I want to mention here is really the number of points that are outside of plus or minus 2 or even plus or minus 3 is not really necessary that much. But what we do is we see a trend there. That's what's concerning to me. Why for lower y hat values are we having essentially negative residuals? Meaning y hat is higher than y, and then y for higher values of y hat. Why do I have positive residuals? Meaning y is greater than y hat. Remember how the standardized Pearson residuals calculate? Y minus y hat divided by a square root of a variance. Why is this happening? And that's of interest, and you would want to try to figure that out. In particular, this is especially this kind of a plot seeing something like this. Let's say you have one explanatory variable x. If you see something like that, where x is now on the x-axis, maybe I'm plotting standardized Pearson residual versus distance, and I see something like that, that tells me maybe I need a transformation of my explanatory variable. Here's another plot. I'm not saying anything about the normal distribution approximation here, if it works or not. We have some points outside of plus or minus 3, but it typically only happens when pi hat's close to 0 and 1. Should we be concerned? I'll give you three possible answers. After all, this is a categorical class. So I'm going to give you 3 categories to pick from. Yes, no, maybe. Maybe, yes, maybe. It depends upon if we can trust the distributional approximations here. And one of the reasons why I bring this up is that especially with logistic regression models, you will very often see something like this. And it won't actually be something of concern. Because the distribution approximations will end up being poor there. You'll see more of that as we go along. Now let's consider again that we have just a chapter 2 model. We have purely binary responses. So explanatory variable pattern form, well, it's essentially the same as my data, original data. Notice the separation that we have in those points there, and we see a trend too. Is this something to be concerned about? Yes, no, maybe. This is often a yes, or it can actually be a maybe. I guess that maybe does both. One of the reasons why I want to point this out is that you will often see this separation when you have binary responses. Now remember what your residual is. Y minus y hat divided by square root of some stuff. So if y can only be 1 or 0, your residuals are very discrete. They're going to be either one thing or another, and then of course you have to factor in the pi hat. And so that separation there does not bother me at all. It's the trend that I'm concerned about. But the separation does not bother me. But do note though that you see some stuff that are outside of this plus or minus 3 here. Again, a standard normal approximation is not going to work well. So you got to be very careful of saying those are outliers. Let's take a look at an example, or an actual example with the Placekicking data set. This is page 544. Okay, let's say that my data is in explanatory variable pattern form. So that's what W.N represents, my data. I estimate the model number of successes, that's my Y, essentially. My trials is my N. And my X is distance. Of course, I weight by the number of trials. Now, what I can do is I can find all my pi hats like we've done before using the predict function. Next, I'm going to find my Pearson residuals and my standardized residuals. Just double check that. Also, what I'm going to do is find my estimated linear predictors. In other words, beta hat 0 plus beta hat 1 times x, or distance. And then lastly, I'm going to put everything nicely together into a data frame. So for example, at 18 yards, I have 2 successes out of 3 trials. My estimated proportion is 0.667. But my model says, hey, estimated probability of success is about 0.98 there. Wow, you're way far off. Take a look at the Pearson residual and the standardized residual. It's outside of our plus or minus 3. But I'm not really concerned about it, because I know a normal approximation is not going to work well here. Notice that the only time that this standardized Pearson residual or Pearson residual will be within plus or minus 3 is when what happens? When Y is?
Should we continue?
When Y is 3. So Y is either 0, 1, 2, or 3. Notice even at 2, we are still having problems. What's going to happen at 1? Well, it's just going to make it look worse. What's going to happen at 0? It's going to make it look worse, even farther. Only 3, only when you observe a number of successes equal to the number of trials will you not have a standardized Pearson residual outside of plus or minus 3. That's the issues here. That's why using a normal distribution approximation is often not good. But even for, let's take a look at 14. I'm sorry, let's look at observation 5. A distance of 22, you have 12 successes out of 14 trials. The proportion of successes is 0.857. The model predicts 0.964. I'm at negative 2.1 for my standardized Pearson residual. So it's a little bit outside of plus or minus 2. And again, you're left with a situation, we have binary outcomes here. And sometimes you're going to miss some field goals, even if you have a high probability of success. And even if I make 12 out of 14, if I were to use a strict standard normal approximation, you might say, well, that's just not good enough. You need 13 or more to avoid that. So even with 14, due to having such a high probability of success there, I'm not concerned about that observation. So what I do next is I do some plots. So I plot distance on my x-axis, standardized residual on my y-axis, and I put in some plus or minus 2 and 3 lines on that plot. And I'll explain the rest of this stuff shortly. And this is what I get. Just look at the plot on the left. That's the middle plot and the plot on the right. The code's in the program. I don't give it in my notes. Ignore the red line for now, or the red dotted line. So again, standardized Pearson residual, distance. And so we can see at 18 yards, hey, that's outside of that minus 3 bound. But again, I'm not worried about it. That was that first observation that we just saw. At 22 yards, there's the one that I pointed out as well. Again, I'm not worried about it. Take a look at this one. That has a high positive residual, and that's at 20 yards. So, I have 789 trials, 776 successes. Remember why we have so many there? It's because of all the PATs. Excuse me. So, I observe a probability of success of 98.4%. My model estimates it to be 97.1%. And we can see my standardized residual is 3.628. So, can I trust the standard normal approximation here? Well, I think we probably can. You know, I do have a lot of observations there, a lot. You know, if I had 50, I might be questioning it, but I have a lot. And here's another reason why I am thinking that this is indeed a poorly fit observation. I can use my knowledge about the data itself. And I know that this data, the reason why a lot of these observations are due to because they are PATs, not field goals. And so what this is telling me is, maybe the reason why this is so poorly fit is because there's a different characteristic about these kicks than the other kicks. Maybe I should have a variable in my data in my model called PAT. And in fact, what we will see in section 5.4, we remove that problem that you see there by including a variable that accounts for if it's a PAT or field goal. And I think, you know, especially from a football fan perspective, I think this is interesting because you know that PATs are worth 1 point, field goals are worth 3 points. You know, how often when you watch a football game does the defense not really try to block that PAT? Before field goal, they tend to maybe try a little bit harder. Take a look at that estimated probability of success. Now note that this is both PATs and field goals are within that 20 yards there. But most of them are PATs. And notice how the probability of success is higher than what the model estimates. And I think it's essentially because of PATs have a higher probability of success than field goals. Truly they do. Any questions about that?
If the pi-r, the estimated pi-r, if it was closer to the overall pi-r for the overall data, would that improve?
Could you restate your question?
So the estimated pi-r is 0.971.
Yes.
So the overall pi-r for making or missing a field goal, if that was closer to the overall pi-r in the data set, would that?
I don't think it's going to make a difference. Are you still talking kind of about the like what would happen with the hat matrix diagonal values?
Yeah.
Now remember, the hat matrix diagonal values are based upon the x's, you could say. We are actually, the pi hats are based upon, if you think of the overall pi hat for the data, that's based upon y's.
Okay.
Okay? But other than that particular observation, if you look at all the other ones, this model seems to be doing a relatively okay job. Now, excuse me. Well, I'll backtrack there a little bit. So you see these red lines here? What I did was I plotted what's often referred to as a smoother to help you see trend. This is a particular kind of smoother called a Loess regression model. If you take a full semester on regression analysis, you learn about Loess regression models there. Don't worry about them here, other than just understand that they allow you to see trend in a simple scatter plot. It's like what we have there. Another thing you have to understand about them is that on the edges, meaning let's say for extreme values on your x-axis, the models are typically not good. So I typically focus more in the middle of the plot to make a judgment about trend. And so we can see that maybe we do have some kind of trend going on there. Now, part of the reason, I don't know if you remember this, but I'm pretty sure we did that, or it's in a homework. If you look at distance squared in this model, it is actually marginally significant. Meaning the p-value is, I don't know, about 0.02, 0.03. And I think what that's kind of then being evident by what you see here, this trend, suggesting that low distances often have smaller residuals, negative residuals. Higher distances have positive residuals, and that might indicate a trend. In particular, one way to handle that is to look, for example, at a distance squared. So if you want to see the actual code that goes into the low-S regression model, you can take a look at that. I'm just expecting you to be able to apply it in a situation. Chapter 11 of my Stat 70 notes talk about low-S regression too, if you want to see it. So also what I did here was I did plots of the standardized residuals versus pi hat, which would be like our y hat. Standardized residuals versus the linear predictor. Now in this particular situation, you can see that you're essentially getting the same plots or a mirror image of the plot that you got from the distance plot. And the reasons being because we only have one explanatory variable. But if we had more than one, these plots wouldn't necessarily all look alike, and they're all helpful to look at, to look for trends. Okay, let's see here. So page 47, let's make sure I talked about everything. So I guess going back to that 20-yard, those 20-yard PATs, we were talking about, well, can we trust that normal approximation? Well, here's another reason behind why I'm fairly confident that this is something to be concerned about. Is, well, how about we use a binomial approximation here, just similar to what we did before. So let's say maybe I look at, well, what's the probability, estimated probability that the number of successes is actually greater than or equal to 776. What that says is, again, it's a measure of how extreme 776 are. Well, that's equal to 1 minus the estimated probability of being less than or equal to 775. And if you use a normal approximation, use a binomial distribution using pi hat for that distance from the model, and therefore the prob argument, you get a probability of 0.0172. So what that's saying is, since that probability is small, it says it is kind of unusual to observe this extreme number of successes. So let's say if there were no potential problems with the model. If there were no potential problems with the model, where would you expect this low-S regression model, the red dotted line, to be on these plots? Across the center. So you might see something like this. Maybe even a little bit farther from the center line, but somewhere close to 0, and really not showing any kind of big trend. Okay, so it takes us to page 48. So the residual measures that we've done so far allow you to look at, for one observation at a time, are there issues with your model? You might be wondering, well, how about just overall for your model? Are there any possible problems? And that's what goodness of fit statistics allow you to make a determination about. And they're quite intuitive then, how they are formed. So we're going to look at two different ones, one called a Pearson statistic. Guess what you do? You just simply add up the squared values of your Pearson residuals across all observations. That's your Pearson statistic. So, you know, what would you look for here if you had some issues with your model? What kinds of values of x squared would you expect to be of concern?
Large.
Large, yeah. Because think of it this way. I have my residuals there. They are squared. So a squared residual indicates a problem with a particular observation. If I have a lot of those, that means my x squared is going to be large, and thus it makes sense that I have a problem with my overall model. Also, you can look at simply the residual deviance. That makes sense. Remember, again, you're comparing your model of interest to the saturated model. And so in terms of the hypotheses that you're looking at, well, that just kind of gives it away. Oh, I'm sorry, I should have done that one. Now, what's the distribution for these statistics? This is tricky. They have an approximate chi-square distribution where you take the number of observations. This is after you've done explanatory variable pattern form, for example. Number of observations, m, minus p tilde. We'll call p tilde the total number of parameters you're estimating. That will then, excuse me. So you can use a 1 minus alpha quantile from this distribution, kind of get a line, a judgment line of, okay, is my x squared large enough to say, yes, there's a problem with my model. Problem, though, is that this approximation, again, is often not good. It's only valid under the assumption that the number of unique set of explanatory variable combinations in the data is fixed as the sample size increases. So what does that mean? Or let's look at a potential place where there would be a problem. Let's say that you have one explanatory variable x. It's absolutely continuous. What's going to happen as your sample size increases? Are you ever going to get the exact same explanatory variable value? No. So then the issue then is that the number of unique explanatory variable combinations is going to continue to increase. And this actually invalidates the mathematical theory behind developing this chi-square distribution approximation. So that's an issue. So because of that, often it's not very useful to use that chi-square approximation. I mean, I will often look at it, and if something pops up, it's like, okay, that's interesting to see that indeed I am greater than this quantile, but I definitely would not use that overall to make a judgment about my model. Instead, a kind of an ad hoc solution to this is to look at what we call deviance divided by df for degrees of freedom. And we look at that value, and we look for large values of that to make a judgment of, well, yeah, are there problems with the model or not? If the model is reasonable, this numerical value should not be too far from 1. Why? Especially stat majors. Why? Excuse me? It will be eventually, yes, but we haven't talked about that yet.
Expected value of the chi-square should be ADF.
Yeah. So expected value of a chi-square random variable is the degrees of freedom, right? So, you know, if I were to take expected value of d divided by m minus p, and if this approximation works, I will get 1. Well, I guess that would be equality if the approximation works. Now, So you might be thinking, well, wait a second, you just told me the chi-square approximation doesn't work. Well, yeah, that can be an issue. But you know, where are you going to see the differences more? In the center of the distribution or in the tails of the distribution? It's the tails of the distribution. So that's why, you know, this is kind of an ad hoc statistic that, you know, you're still kind of using that chi-square stuff, but not totally. You're just simply using this first moment. And so, well, how far away from one is of concern? Well, this is where you can do the old, you know, what you learned in your very first stat course, that all data lies within plus or minus 2 to 3 standard deviations from its mean. So what I can do is, look, here's where that mean should be, plus we'll do 2 standard deviations. If I have a deviance divided by df that's greater than that, okay, there might be a problem, because that will be unusual to observe if the model truly worked. If I am greater than 3 standard deviation, uh-oh, I'm really concerned. This is an ad hoc procedure, but it's better than nothing. Just realize that. Okay, so that takes us then to page 550. So we've talked about how to judge if a particular observation is poorly fit by the model. We talked about how to judge if, let's say, a lot of observations are poorly fit by the model. Now we're going to look at a situation where perhaps an observation is fit well by the model, meaning its y is close to its y hat. But maybe that observation is maybe that happens because that observation is influential, meaning that it has way too much influence on deciding what the model is. Well, what do I mean by that? Let's say that we have a simple logistic regression model, and this will be an extreme example, but I think it will prove the point. Oh, well, we'll put actual numbers here. So suppose that this is my logistic regression model. Now let's say I remove one observation from my data set and re-estimate the model, and everything's the same, except for now I get a negative 10 there instead. Whoa, this has totally changed my interpretation of the effect that X has on my response. Was this observation then that I removed from my data set, was it influential? Yes. And so measures of influence then are based upon this same concept. Let's remove an observation from the data set, re-estimate the model, and look, do things change or not? If things don't change a whole lot, hey, good. That observation is not influential to determining the overall model itself. But if I see a big change, that tells me, uh-oh, I have an issue. And then you have to make a decision about what do you do about it. We will have a great example of that in section 5.4. So stay tuned about what we would do about it. But typically, you know, you want to avoid situations where you have a very influential observation. Because again, what it says is, if you didn't actually observe it, your decisions about, you know, your model, your problem of interest would totally change. And so typically, you would not want to have an influential observation in your data set. Now, let's say that I have a sample size of m. You know, based upon what I just told you, if I had to remove an observation out every single time and re-estimate the model, that would mean I might have to estimate m plus 1 different models. Fortunately, you don't have to do that. Instead, there are nice approximations that are made to that process so that you only have to estimate one model overall. And using those approximations, then, we have some statistics that we can look at to make a judgment of is a particular observation influential or not. The first statistic is called Cook's distance. Cook is Dennis Cook. He is a professor at the University of Minnesota's Department of Statistics. I believe he's now their department chair. One reason I like to bring him up is because he happens to be a Kansas State University graduate, just like me, but just from a long time ago. And anyway, so he's probably one of the definite leaders in regression modeling research. He has done a lot. That's how you get something named after yourself. And so this is what Cook's distance measures. It looks at essentially all parameter estimates. How would they change if the mth observation was removed from the data set? And the statistic that measures it, we call it CD sub m. And you just simply take your standardized Pearson residual squared times your hat matrix diagonal value divided by p plus 1, where, and I need to be careful about that, sorry. P is equal to the number of parameters for your model. No, unfortunately, that's a little bit inconsistent because I was using p tilde before. We had some issues with trying to be consistent with how to indicate the number of parameters. Because we were often using, let's say, like in chapter 2, we had x1, x2 up to xp. What happens if you now have a categorical explanatory variable? How do you include that in there and stuff? And so, unfortunately, I think this is a place where we were not very consistent. So p plus 1 times 1 minus h sub m squared. This value is always going to be greater than 0. And basically, the larger the CD is, the more influence a particular observation has. So the larger, the more influence. A general guideline is, well, if you have something greater than 1, well, maybe this is influential. If you have something greater than 4 divided by m, maybe this is influential. There's not necessarily a set guideline, but these are often what's used. Another measure that you could use is what's called the change in the Pearson goodness of fit statistic. That kind of makes sense to do, because after all, the Pearson statistic that we were looking at measures overall how good is your model. And so if you remove an observation from the data set, re-estimate the model, and let's say x squared changes a lot, maybe it was, let's say, maybe it was 10 with all of your data, and then it drops down to 3 with all your data except for that one observation. Then it says, okay, that's a big difference there. Maybe this observation is influential. And so the delta x squared statistic then ends up being just simply your standardized Pearson residual squared. That's it. So essentially, the standardized residual ends up measuring two different things, both looking for outliers and influence. So that's nice. And you can use a chi-square-1 approximation, hopefully with it. Remember, a standard normal random variable squared is a chi-square-1. That's where this comes from. Anything greater than, let's say, maybe 3.84. That's a 0.95 quantile from a chi-square-1. May indicate, yeah, you have an influential observation. But again, you have to be careful about trusting this distribution approximation. Oftentimes, it's not good. So what I typically do is look at like thresholds of 4 and 9. If I have something above 4 and 9, I start getting a little worried. But I will look at the observation more closely to see, well, can I trust that approximation or not? And lastly, we can look at the change in the residual deviance statistic. We're going to call it delta D, and that's how it's calculated there. And I guess one more thing here. Then I do talk about the hat matrix diagonal values here. As I was talking about before, it's a measure of how far is a particular values, let's say explanatory variables, from the center of all your explanatory variable values. If your hat matrix diagonal value is large, that could indicate that this observation has influence and potentially could be detrimental. The key is it may not be detrimental, because large values of a hat matrix diagonal value does not mean it is detrimental for reasons that I mentioned before. There are particular guidelines that you can look at. I personally don't typically look at the hat matrix diagonal values much. My co-author likes to at least look at them. And so as a compromise, we included some discussion in our book, but I don't think that they're you have to be very careful with it. I think sometimes they can cause more detriment by looking at them than what they're worth, especially since we have other good measures to look at. Okay, so how do you do these calculations? Well, guess what? We have nice little functions that are set up to do these calculations. So hat values calculates the hat matrix diagonal values. Cooks.distance calculates the CD values. And again, we can use our standard to get some of these other values too. In section 5.2 of my book, we put together a general function that can be used with chapter 2 and also chapter 4 called GLM INFL diag, which automatically calculates some of these measures. You're welcome to use that. But for chapter 2 models, I recommend instead you look at a particular function that I wrote for section 5.4. Because it gets at some of the specifics that you definitely need for like logistic regression that you wouldn't need necessarily for Poisson regression. And this is the function, examine.logistic.reg. That function, this is kind of looking ahead the next page, is located inside this program that's on the book's website. And so just run the program and you get the function there. We'll talk about the function more probably next time. Okay. Excuse me. So let's take a look at another example that corresponds to what we were looking at before when we have 50 points plotted. In here I have plotted my delta x squares, which again is r sub m squared. I plotted it versus pi hat, which would be like y hat. Now, of course, since I'm squaring these standardized Pearson residuals, they all have to be positive. And so this plot here is essentially another representation of the plot that we saw on page 5.43. Let me go back there. Okay, remember that plot? Okay, and what did we say? Well, this is not necessarily something to be concerned about to have these values outside of this plus or minus 3. And the reason being is because that standard normal approximation often doesn't work there. So when we take a look at it, then in this perspective, it's just a squared version of it. And so I'm bringing this up because this is one of the most important plots to look at in this my function that it creates, because it allows you to evaluate influence and essentially outliers at all the same time. And you will typically always see these guys right up there. And often, very often, they're not something to be concerned about. Also something that you will see too, so notice this pattern. Did you see that pattern there? That's also something not to be concerned about. It's just simply due to the discrete aspects of this data. It's not necessarily something to be concerned about at all. Okay. Oops. So that takes us then to using this function that I've written with respect to the Placekicking data set. Now, the stuff that I do here is not in the book, at least for, in section 5.4 we will look at this data set a lot more closely, and I just chose to write up another program because I want to just look at the model with respect to distance itself, because I think there's some interesting things to see. And so this program's on my website, my course website, not the book's website. But unfortunately we are out of time though. We're not going to have an opportunity to look at it. Are there any questions? Okay, then that's it for today.